Okay, continuing. The native state, a folded protein, is an ordered structure, yet protein folding is a spontaneous process. How is this possible? So, what does this statement mean? What we're saying is, and we've shown this previously when I drew the sort of a pathway, right? We said we had an unfolded state for the protein and we had a folded state down here, right? And the protein will move down this state to the folded state, from unfolded to folded, and that this difference between the folded state and the unfolded state is a delta G. And obviously, this has a delta G less than 0. So it's a spontaneous process. It will happen without any input of energy through coupling with another reaction or process. Now, I think we can all agree that a folded protein seems like it's a much more structured molecule than an unfolded protein, because an unfolded protein is just a polypeptide chain. It's sort of unfolded, right? And then this thing will go ahead and fold into some sort of structure with beta sheets and alpha helices and etc., right? By all appearances, this seems much more structured than this. So if I was going to look at it, I would think that, well, the folded protein has lower entropy than the unfolded protein. So how can that happen? Because we said that going from low entropy to high entropy is favorable, whereas going from high entropy to low entropy is unfavorable. Well, we're about to answer the question of why water minimizes its interaction with hydrophobic surfaces. So we'll read through this first and then go over it piece by piece. A hydrophobic surface will force water molecules to form an ice-like cage around the hydrophobic surface. Ice-like cage. At physiological temperatures, water is a liquid, where it is hydrogen bonding with itself. As a rule, charged atoms, whether an ion or as part of a molecule, and this can mean fully charged or partially charged, must interact with a countercharge so that there is overall neutrality. A state where charges are not countered is a high energy state, and this is what we covered in the last video. Water cannot form any hydrogen or ionic bonding interactions with a nonpolar surface. Thus, its degrees of freedom is reduced because it cannot turn its hydrogen or oxygen toward the nonpolar surface. Therefore, it can only rotate on a plane, two-dimensional plane, instead of in 3D space. This leads to a single molecule width sheet of water wrapping itself around a nonpolar surface. This is a low entropy state as compared to water molecules not interacting with a nonpolar surface. Water molecules will minimize their interaction with a nonpolar surface, decreasing the amount of ice-like cages and therefore increasing entropy. Example, mixing water and oil. Okay, so let's take a closer look at this and explain what is going on. So I am going to draw this surface right here. And this surface is hydrophobic, okay? This red panel with the red lines going through it, imagine that this is a hydrophobic surface. Now, I'm going to also draw it from the side. Okay, so here is that same surface from the side, okay? So now a water molecule in solution can easily rotate in 3 dimensions, whichever way it likes, and hydrogen bond with other water molecules. Let's just worry about water molecules and not any other hydrophilic molecule that is in solution, okay? So it's just hydrogen bonding away, right, with other water molecules. And they have full degrees of freedom, meaning they can rotate in any direction they want, and they can still hydrogen bond with each other. Okay? But now, when the water molecules get near this hydrophobic surface, if it approaches in this orientation, well, the hydrogens cannot hydrogen bond with that nonpolar surface. And if it tries to come at the nonpolar surface in this direction, well, the oxygen cannot hydrogen bond with the nonpolar surface. And it cannot hydrogen bond with anything else. Basically, if it comes at the surface in these two orientations, the hydrogens here cannot hydrogen bond with anything, and the oxygen here cannot hydrogen bond with anything. So it's basically left with only one solution. Because the oxygen cannot be facing the nonpolar surface, or the hydrogens cannot be facing the nonpolar surface, it must lie flat on that surface. So now I'm going to go to the other panel. So the water molecule has to lay flat like this, so that another water molecule can come along and lay flat also, and another one, and another one, and on we go, right? And you're going to have hydrogen bonding interactions happening. It might be a little bit harder to see now, but maybe red wasn't an amazing choice for this, but I think you guys can see it. So what you get is this one molecular width sheet of water on that nonpolar surface. Well, this is very much like ice. You have a one molecule width layer sheet of ice wrapped around this nonpolar surface. Well, this is very structured. This is much more structured than water being able to freely rotate around, like here in solution. So this right here is a very ordered structure by water molecules. So low entropy. Whereas this right here, water in just an aqueous solution not being even near a nonpolar surface, is high entropy. Maximum entropy that water can really achieve. To maximize entropy, the water molecules will spontaneously try to move from this state right here to this state right here. So you can think about it in this way. Minimizing interaction with hydrophobic surfaces, it's equal to minimizing ice-like cages, which are low entropy. So yes, the protein is more structured when it's folded, but when it's folded, the hydrophobic surfaces, the hydrophobic side chains, are also away from solution in the hydrophobic core. And when they're in the hydrophobic core away from solution, there are no ice-like cages. So if you have less or no ice-like cages, you've minimized the interaction of water with those hydrophobic surfaces to zero. So you have decreased entropy when the protein gets its native state, but you've also increased entropy more, so bigger arrow, by minimizing ice-like cages. Minimizing or removing ice-like cages. So overall, you have increased entropy. So in the case of mixing water and oil, obviously you're not minimizing the interaction with the hydrophobic surface to zero, but if you look at this, mixing water with oil, here it is my containers. It's the same container. Imagine that they're the same size. I know I'm not drawing this perfectly, but here's water, and I have a little bit of oil. The oil is red, right? And they're separate. Now I mix it vigorously, right? Mix. And what I have is, I have the water, but now, and I'm not really drawing this to scale because if you mix really well, the spheres of oil are hard to see, but that's what you have. You have little spheres of oil everywhere. They're going to be much smaller than this initially. And once you stop mixing, those spheres will come together and you go back to this. And this will be spontaneous, meaning that you don't have to do anything. Once you put the glass down or the jar down, oil and water will separate, right? Now, if you were to calculate the surface area that water is exposed to when in this state compared to this state, the surface area of contact between oil and water is much larger here and much less here. And really, this is just a geometry problem. It's easy to do. I've done it before, and the math works out. You just have to take total volume of the cylinder from this side and decide how many spheres you want. And then you figure out the area of the sphere and the area of contact with one side of the cylinder with water. And it works out where it's always less of an area of contact when they're separated compared to when you have little spheres. During protein folding, hydrophobic side chains are excluded from solution by water molecules in an attempt to minimize surface area of contact between them and the nonpolar surface, and therefore increasing entropy of the system, the protein, and the aqueous solution. The increase in entropy by the exclusion of nonpolar surfaces from the aqueous solution is greater than the decrease in entropy from protein folding into its native structure. So overall, the entropy of the system has increased, thus the process can go forward and happen spontaneously. Alright, we'll stop there and continue later. Thank you guys.